Okay, folks, section 3.1, this will be my second video. Just reiterate our power rule, which was discussed in the first video. And then I wanted to introduce a couple of other basic rules that go towards polynomials, which are really combinations of power functions with maybe some constant multiples. So we'll talk about the sum, difference, and constant multiple rules. All right. The power rule, what we saw in the previous video was this. The derivative with respect to x of a power function, x raised to some power, raised to some exponent, which we're calling n, was equal to n times x to the n minus 1. All right, so in other words, we said this rule is if I've got a power function, let's bring down the exponent as a coefficient, and then let's decrease the original exponent into our new exponent, and there we go, then we've got our derivative. Okay, so that's the power rule. Let me talk about the constant multiple rule. So I kind of wrote these out of order, but I want to come over to that one first. And then what I'm going to do is sort of build that rule into the power rule, kind of combine them into one and the same operation or one and the same process that you guys carry out, because that's really the way it works. What the constant multiple rule says, I'll write it in the D notation, then I'll give an example. So what the constant multiple rule says, if I want to do this, the derivative with respect to x of, and I'm going to put the function inside here, right? So let's say the function is a constant times some function of x, right? And now this function of x, in this case, the first example I'll do is going to be a power function, but this constant multiple rule works for any function, any differentiable function, f that I plug into here. And this is a nice rule. It basically says if I want to do the derivative of a constant times some function, then let's just do the derivative of the function, right? So I'm just going to take the derivative of the function and then just multiply the constant by that derivative. All right. So in other words, another way to say that is that sort of the constant comes through the derivative process. That's the way I like to think about that. All right. Let's look at an example of this. Using our power rule, if I said this, the derivative with respect to x of x cubed, right, is equal to, so we covered this in class together. We looked at this in the previous video. And according to this rule now, it says bring the exponent down out front. So we get 3, and then times x raised to the 3 minus 1, so 3x squared. All right. So there was no constant multiple out front here, though. I just had that. All right. Let's say I did this, the derivative with respect to x of, let's say I have 5x cubed. Right. That's what I want to find the derivative of. Well, what they're telling us to do here, according to this constant multiple rule, is to basically just pull this 5 way out front. So whatever my answer is going to be that constant 5 times, and then the derivative of this x cubed. So then 5 times the derivative with respect to x of x cubed. Okay. So I know some of the early examples from homework 3.1 had you kind of interpreting polynomials like this, sort of splitting it up. And some folks were emailing me, sending me ask your teacher messages. They were filling 3x squared in right there, right, for the derivative. So they were kind of doing the process. Really what we're doing, though, is sort of just rewriting the problem first and then take derivatives, right? So this is saying if I want to know the derivative of, and forgive me if I don't always say with respect to x. I should say that. But basically, since x is our only variable here, this little notation is saying take the derivative of the constant 5 times this function x cubed. And what the shortcut says is then the answer is whatever the constant is times the derivative of x cubed. Now, what's the derivative of x cubed is 3x squared, right? So we get 5 times 3x squared. And then last thing we would do is multiply those constants together, right? 5 times 3 gives us 15, so we end up with 15x squared. Okay, so kind of easy to use. A lot of folks combine this constant multiple rule with the original power rule, and they kind of combine it in their steps when they're showing work, and may not even realize they're combining it. It just seems natural. Okay, so let's think that through. What are we told to do? We're told to bring this 3 down out front, right? So the 3 as the exponent eventually lives out front as a coefficient. Then this 5 is coming through the process. And so ultimately then eventually, since they're both coefficients now, we multiply those coefficients. So 5 times 3 gives us the new final coefficient, in this case of 15. So you can kind of attach these two rules if you like. They're really two separate rules. But if I want to take the derivative with respect to x of, let's say, some power function x to the n that might have a constant sitting out front, right? So like we just look at 5 times x cubed, right? So we can write this in the arbitrary sense. And so what ended up happening, sort of the slow method of doing it, was we ended up with we pulled the constant out front, c, and then the derivative of this guy was n times x to the n minus 1. All right, and then eventually you're going to take the c and n, that 5 and 3 that we had in the example, and multiply them together, right? So you can kind of think of it like that. So here, if I have an exponent and I have a constant, then the end result is that those guys are going to be multiplied and become the new coefficient. Okay, so let me kind of run one like that. An example. So let's say I've got 7x to the 8th. Right, and I want to take the derivative of that. I'm not going to write 7 times the derivative unless the web assignment is making me show step by step by step. But let's just do the process. My end result would be 7 times, and then I would bring this 8 down. So times 8x raised to the 7, because I would decrease that. But then I'm going to have a 7 and an 8 sitting out front, so I'll multiply them. So this 8 times that 7 is ultimately going to give me 56 x, and then decrease the power still to the 7. All right, so I kind of did that instead of writing 7 times 8x to the 7th. That's sort of the mechanics that are happening right there. But yeah, sort of combine those rules for a nice little shortcut, and that works fine. Okay, so we've got our power rule, we've got our constant multiple rule. So those are helping for polynomials. So again, things like this, 7x to the 8th. That looks like maybe one term that we might have in a polynomial. However, polynomials essentially are either sums and or differences of different power functions, right? They're different power functions that have been added or subtracted together. And so the nice thing about the derivative process is that through sums and differences, meaning if you've got plus or minus signs attaching to terms, the derivative kind of just extends or sort of distributes, spreads out to each term individually. I'll warn already though, that's not the case for products and quotients. So you probably notice there's another section coming up called the product rule and the quotient rule, right? Meaning multiplication and division. So we're not covering those there. Those don't work as nice as these are going to work. Those have special rules where we combine different functions and derivatives, and they're kind of messy to work with. These are straightforward, okay? So the sum rule, the derivative with respect to x, if I've got a sum of two functions, f of x plus g of x, all right, a sum of two functions, which oftentimes we think of that as itself a new function, right? So you might be given one function that's maybe called f, or one function that's called something, but you notice that it's a sum of two different things, or several things. So I'll do some examples in a second. But what's nice about this rule is it's just the derivative of the first piece, so derivative of f plus the derivative of g. Okay, so that's, you don't really say distribute in this sense, but it's kind of like that. This denotation gets applied to the f and then also gets applied to the g, and then we just take each derivative individually and add them together. All right, so this is the sum rule. Let's look at an example. If I have let's say x to the 5th plus 2x to the 4th. All right. So again, in the WebAssign, sometimes what they do is they make you distribute this out and break out the constant and so forth. So in notation, what you might be doing here is saying this is the derivative with respect to x of the first term, x to the 5th, right, plus, so then I'm going to add that to the derivative of this thing. And if I'm going step by step, I'm pulling the constant out, so the derivative of that will be 2 times the derivative with respect to x of x to the 4th, okay? So everything I've shown here, you kind of do this in your head. WebAssign, through some of the examples, makes you kind of show these steps. What I've done here is I haven't really taken any derivatives yet. I've sort of just reorganized and broken down piece by piece what the original problem is asking me to take, okay? And I haven't taken any derivatives, which is why I still have this denotation. So now this says the derivative with respect to x of this guy, which I'll use my power rule, 5x to the 4. And then I've got the derivative with respect to x of this guy. So x to the 4 is going to give me 4x cubed. Multiply that by this 2, and I'm going to end up with an 8x cubed. All right, so that's our final answer. Right there. There's our derivative. Okay? So again, I think most folks kind of just do this without really realizing that they're using the sum rule. They just sort of distribute it and take those things. And again, let me emphasize, if you're not asked to show all this, it's good that your mind thinks that this is what's happening. But I think most folks would just jump in, grab a different color here, just jump in if they're asked this question and just do the process. So the derivative with respect to x of this guy is the x to the 5th gives me 5x to the 4th. This thing, I'm going to bring the 4 down, multiply it by the 2, so get 8x cubed. And then the original two pieces were being added, so the result got the addition symbol in there, and that's it. Right? So it doesn't have to be painful like we did over here, but there we go. Same final answer, same process. All right. That's our sum rule. The difference rule is no big surprise. If you've got a minus sign instead of a plus sign, then you just keep a minus sign with your derivatives, and that's it. So let's just, for the sake of time, say that was our original function, x to the fifth minus 2x to the fourth. The derivatives of each term by term, is the same thing, right? The only thing different now is I'm subtracting those terms. All right. Simple. And now if I've got a polynomial, poly actually means many, although you can have polynomials. So in other words, x squared is technically a polynomial. Sometimes you call that a monomial, though. Mono meaning one. A binomial, x squared plus 3x, right? So binomial, I've got two things. Trinomial, got three things. But generally speaking, a polynomial, if you've got several terms, you just go term by term, right? So if I had this, if this is my function, kind of at the bottom of the board here, switch back to prime notation. If this is my function, f of x is x squared plus 3x minus 5, then I just go through my derivatives step by step, piece by piece. So derivative of x squared gives me 2x, right? Derivative of 3x is just 3. That was one of the examples that you can use your power rule, right? 1 times 3 is 3, becomes my new coefficient. X and then x to the 0, right? Because I subtract 1 from there. But x to the 0 is just a 1, so I don't really need to show it. Another way to think about that is 3. If you're just looking at this function, 3x, that's just a straight line with slope 3. So the derivative tells us what the slope is. Slope is 3. There's a plus sign, so put a plus right there. All right. And we looked at this one in class today, or class one day. If not this number, just a constant. The derivative of a constant is 0. Okay, so I can put a 0 there, minus 0. And that looks fine as my derivative. Do I have to write minus 0? No. So that also looks fine as my derivative. All right. So again, though, you just distribute your derivative across plus signs, across minus signs. And there we go. All right, guys. The very last thing to mention from section 3.1, so my third video will touch on that, is the derivative of exponential functions. Okay, e raised to the x. So while I'm discussing the power rule, actually, let me just stop there, and then that'll just pick up for video number 3. Alrighty, guys.